CLion, a cross-platform IDE for C and C++. Download now.
Welcome to my talk on C++ sys. Essentially, it's looking at creating a new approach to developing a standard library to facilitate safety within C++. So let's begin. So essentially, the core problem is, C++ is designed with this close relationship with C, which is, fantastic, direct interrupt, no bindings. But the disadvantage is, safety isn't guaranteed. We're making great standards, certainly we're making great strides, certainly with the newer standards. But, essentially there's still some issues, and there's still ways that it has a name for itself of being, an unsafe language. So essentially, it generally boils down to a wide range of these memory errors are basically due to incorrect, lifetime management. So potentially, dangling pointers and things like that are generally caused by, the memory lifespan not being correctly managed. What's worse is that many of these are non-deterministic and environment dependent, which means that, they're very difficult to track down and they're difficult then to resolve, and they end up just appearing in the worst possible time, in front of stakeholders and things like that. So let's have a look at some sample code, and you can see that it's effectively not going to be that easy to track down, even in a simple example like this. So let's go through it. So essentially, we have this global bombs vector, and I'll explain why we're using a global in a second. We're basically pushing back, a bunch of bombs, and then we're going to touch the third bomb in the array. The touch, dutifully clears the bombs array, presumably emulating some kind of explosion. And then it prints F, crikey, the bomb was set off by, and then the bomb name. Now, can any of you spot what's wrong with this? So let's try actually looking then at building it and seeing where we're at. So this is the code. So it's basically the same as what's on the slide. And if we build it, so we'll probably have it here somewhere. Oh, that was the old one here. So I'm just compiling it. This dangling, then the standard example, and we run it. It just ran and it finished. That's great. There's no problem. Except, there is actually a problem. And as we can see here, effectively, we're clearing the array, which means that essentially, the current one that we are, calling touch on, so this, the implicit this variable, it's effectively now dangling. And we're, on line 13 where we're really hitting it, and that this M name is no longer valid. So, and I'll explain, how C++ sys resolves this shortly. So first of all, the answer could have been, oh yeah, just don't use a global, which is fair. But, effectively you can easily invalidate without globals, and the same issue happens. So for example, imagine this, touch function. Let's say the actual bombs array wasn't, or vector wasn't, global. We generally have a back pointer to the world, which would then contain the bombs. And there's many different ways we can invalidate this. So the explode bombs function, would effectively, clear the array in the same way. The add bomb would push back a new bomb, which potentially would, invalidate the data still as it, copies and reallocates to a new, larger block of memory. Or simply get bombs to return a reference to the bombs array, and then you just call clear on anyway. So that's no good. Or you could, ban sort of like back pointers, from your design, which is fair. So you pass through the game, top level into it, some sort of tick, in which case you're here. But then you could then simply go down to the world and then call all of these functions and invalidate bombs that way, or potentially even reload. So there's basically so many different ways that bombs array could end up being, invalidated. So we really do need to start looking at being able to track this. So the existing approaches, I'll go through them quite quickly. Address sanitizer, an absolute lifesaver, and Valgrind. These are very good, and effectively safety in C++ is a layered approach. There's no perfect solution, but I would say out of all the pros and cons, the biggest issue is that they verify blocks of memory rather than verifying the lifetime, and this is quite important. It has no context of what the actual data or the actual lifespan of that data. Some other approaches, static analysis, these are also good, but they do have their limitations. LLMs are, quite impressive at the moment, but when it comes with, very complex software, they can't really always fit it within the context of the memory. So there's issues there as well. And then, we've got these hardware-assisted approaches. I haven't managed to get hold of either of these. So effectively, that's the biggest con. They're not really, available to everyone yet. So this is where C++ sys entered. And it comes with, and I'll explain a little bit more about exactly what it is, but it comes with two rules. All memory must be locked during lifetime of access, and pointers must never dangle. Even if, quite safely you never access them, they must still never dangle or become, invalid. So essentially, what is C++ sys? It's an alternate standard library. To an extent, it provides a small subset of the standard library. I'm not able to really clone all of it on my own, but it covers a large amount that specifically deal with safety and memory safety. So the stuff in memory, so shared pointer, things like that. It's not an exact drop-in replacement. An early prototype was, but there needs to be some deviation from it. But it is close in many areas, so it isn't that difficult to refactor a code base to include it. Importantly, it's completely agnostic, so it can work with any standards compliant C++ compiler, even some of the MS-DOS days where they weren't quite so standards compliant. So from C++ 98, you can run that with badge of honor, all the way to C++ 20, things like that. But also freestanding, so for things like the embedded platforms where you don't have a full C++ implementation, the standard library, and also then traditional desktop. So it can run on GCA VR, so bare metal, Zephyr, even things like the Mega Drive and MS-DOS with some of the, let's say, newer compilers like OpenWhatCom 2 and things like that. But the key piece is that effectively there is some overhead, but the trick is in the release profile, you can actually strip it out entirely. So effectively, I'm going to say zero overhead. Obviously, that's a little bit of a cheat in some ways, but in other ways, it doesn't really matter. You want to validate it or verify your memory during the debug phases. Do as much branch testing as you can, and then potentially strip it out. You don't need this sort of extra validation for some use cases. So how does it handle it? So first I'll show you the example of compiling it with C++ sys. So you can see here that the code is almost identical. The headers have changed slightly, and std has been replaced with sys for most things, so vector, string, things like that. But the rest of the code is literally identical. So let's compile and run it here. And effectively, the -i is just to say, start including, search in this directory. And that's basically because C++ sys is entirely a header-only kind of library. There's no other dependencies, which is nice. Just like put that out there. So let's run it. And you can see now that it is, deterministically actually, crashed. It hasn't run. It's basically said, there's something wrong. And it's attempting to destruct locked memory. So this is different to the other one, which just kind of worked, even though it was invalid. So let's compile and use this with, let's write for a debugger. And print the backtrace. And you can see what's happening here. So in main, it's calling touch. It's calling the clear function. It's checking this lock, and quite how this lock is applied is quite interesting, and I'll cover that in a second. It's trying to reset basically what's known as this critical pin, which is part of the locking mechanism. And because that already has effectively a reference, essentially, it's now giving out a deterministic panic, attempting to destruct lock memory. That's important. It means every time you run it, it will crash deterministically, which means that it won't just crash in front of a stakeholder or when you're demoing it. It will always crash during the debug stage. So how does this work? Just clarification. So here we're locking the bombs, literally here, and I'll explain how that works in a second. And then when you clear, the bombs vector is locked, so it will always panic. So before I go on to it, let's try it with another example here. Effectively, it's a similar process. So we're creating this one doesn't have any globals. This one, we have values. We're pushing a value back. And then effectively, we have this duck function, which is short for duplicate, where it passes in effectively a reference to the first value. And then values as a reference to that, vector. So you can probably see what's going wrong here as well. So values push back means that's fine. It's pushing back that value. But by then, because we've modified the actual array that is the backing store for this reference itself, references aren't saving it. It's not just pointers that potentially are unsafe, the references as well. So this is now effectively a dangling reference. So the issue being, and again, if I just compile this, which example it is vec invalidated SCD. So if I run this, you can see it just ran. There's no crash there. And likewise, if I do the sys version, I run it, and you can see attempting to destruct locked memory. So effectively, the error is line 5. So the first pushback is fine, but then the reference is now invalidated. So the second one, you're pushing back effectively invalidated memory, which is no good. Or you're accessing invalidated memory to copy it, to push it back. So bounds checking alone is insufficient. As you can see, I dutifully did use at, which means, it's not out of bounds. That is fine. It actually becomes invalidated, at this point. So the bounds check was fine. So that's no good. Or rather, it's good, but it hasn't solved this issue. So instead, the approach is to intercept the actual, array position. So effectively, we pass in 0. Instead, we intercept that, and we use conversion constructor to basically make this an object. I'll show you how that happens in a second. So this RAII object masquerades as the actual index, the integer, or the size t. But because it's an object, we can tie the lifespan of the data, so effectively, the vector backing store, to the lifetime of that object. And then obviously, that has overhead, but we can then strip that out effectively in the release profile, which is important, because otherwise, you'd be running with that permanent cost. And in some ways, just bring up the code. So in some ways, if this was, at, that's a permanent cost. You're now always doing bounds checking. So basically C++ sys, this is still bounds checked, but only in the debug profile. So yeah, this here then is basically, the index, but it's then used as the lifetime object as well as. So that deterministically locks the actual vector basically just before the call of duck, and then release it just after, when then this temporary goes off the stack again, or goes out of scope. So conversion constructor, let's cover a couple of things. So let's start with just employee. So with the employee constructor, we'll ignore this one, but effectively this version takes a size t as its ID. This is the conversion constructor, which means for this jump function, which takes an employee, essentially, you can just pass in 9 into it instead of an employee with a constructor of 9. I mean, I don't like that personally, but that's just, them's the rules. So it means that this ends up creating an employee with this constructor passing 9 in for the ID, and it just works. The same principle works literally for the subscript operator. So, it didn't render that well on this. Zoom in a bit. So essentially, here, it takes in not an integer, but an index lock. But because this index lock has a conversion constructor that takes in a size t, that will just work. So effectively, we can now pass in, 9. This will be promoted. I don't know if that's the right word. This will basically have an index lock object created. And then effectively, it's this order. So it, creates the index lock object. This subscript operator then tells it to lock the vector. The sum function calls, and then the destructure of the index lock happens as it goes out of scope, and then it unlocks the vector again. So yeah, essentially here, the object is locked, or the vector is locked, specifically here, kind of. And then when I push back, I can't even push back the first one because it's basically saying the vector is locked. You can't modify it. And the same approach works for, the C star strings to extract that from a string with C_str, but it works with default parameter. So effectively, it's almost like it taking a parameter of type void lock, but this isn't quite as interesting. So let's look at a similar process, but in a slightly different way. So in this example, let's go through it. We have, again, a global, just because I didn't want to add too much boilerplate code, but we basically assign star employee to be, a new instance of an employee with make unique. We then call retire on the star employee. This retire function, says, right, we need a new star employee. It's a bit of a contrived example. I do apologize. So now Fred is the new star employee. And then we basically printf, James has passed the award to Fred. So we dutifully pass in, the M name, so this M name, and then the new star M name. So where do you think the error would be? So let's just compile and run it. Let's clean up this a bit. So in this one, it is samples. I think I can't remember which one it is. Unique invalidated. So this is pretty much the same code as before. I just compiled it up. So let's run it. And it does actually crash this time, which is good. Let's hope it keeps crashing, because that's a lot easier to find a bug when it actually crashes. And then let's have a look at the sys version, where effectively, again, the code is exactly the same. Now, I actually don't have a unique pointer. I have an auto pointer, but it's very different to the original auto pointer. Actually, it's not. It's just the containers that sys provides support auto pointer safely, or rather the sys auto pointer. So anyway, the same approach happens, but let's actually compile up and run this. Run it, and you can see, the classic attempt to destruct lock memory, all well and good. So essentially, the error, what's actually happening is, this has been invalidated because this star has been replaced, so no longer holds onto the lifespan of the original employee James. So that's effectively deleted. So effectively, this that we are currently in has effectively been deleted. So it's a dangling pointer. This is a dangling pointer. So when we access m_name, we're really accessing this arrow m_name, and this, as we know, is a dangling pointer. So that is obviously invalid to do. So exhibit C is basically this is invalidated mid-method. And you can see that, we used a unique pointer, but unique pointers can't actually verify the actual lifespan of access. It manages the data lifetime, not the access lifetime. So effectively, when it became invalidated halfway during the access, it had no way of defending that. Same with standard shared pointer and the standard auto pointer, but I won't really mention him. Weirdly, the standard weak pointer does actually prevent the issue, or it sidesteps the issue, because you need to call lock on it to basically get a shared pointer to actually before you can dereference that. And it's that shared pointer that emerges from lock as a temporary that actually prolongs the lifetime. But this is a side effect, and to be honest, it's useful, but it does have a permanent cost. Yeah, okay. So how does C++ sys deterministically highlight this issue? It actually injects a temporary object in the dereference operator, and it uses recursive chaining drill down technique, which I'll show you in a second. And it basically binds a lifetime of that object. Sorry, it binds the lifetime of the access to that temporary object. And yeah, so all smart pointers that sys provides, so the auto pointer, which is close to more close to shared pointer than unique pointer, and then sys pointer, which is a strict observer. It means if this is pointing at something and it tries to go out of scope or tries to delete, this will then cause a panic. Or then the weak pointer, which is a weak observer, which basically just gets set to null if the original object it's referring to goes out of scope. So it's actually a similar mechanism. If you do a different dereference here operator, it'll also create a temporary object which will lock the object we're accessing for the lifespan of that access. So recursive chaining, how it works, most of you will know this already, but essentially if we start down here, let's make that a little bit bigger. It's nice and pixelated. So effectively we have a shared pointer, so the standard shared pointer employee. When we call the dereference operator and call jump on employee, it's actually doing two things. It's first returning the underlying raw pointer that's held by the shared pointer, but it's also then dereferencing that raw pointer. So it's effectively doing two things. So you don't need to specifically do anything like that. It happens all behind the scene, and that's basically that that recursive chaining in operation. So we actually leverage it, and we essentially add a third arrow here if you were able to type it out manually, in that we have our our type. So for now it's just auto pointer, a sys auto pointer employee, and then when we do this dereference operator, it doesn't return as the raw pointer, it returns as a pointer lock object, and that's the one that holds the lifespan of the object, or locks the lifespan. Locks the object for the lifespan of the access. And then that object here then returns, or then dereferences the actual object, returns the raw pointer, and then that you can then call the function on. So again, quite a lot of overhead, but again, this gets stripped out in the release build, so it really isn't a problem, because by then you've done a lot of the testing, and the overhead is still pretty good because it has more contextual knowledge. It doesn't need to worry about canaries and things like that on the raw blocks of data. It's still very comparable to address sanitizer and things like that. I'll explain a little bit more about that as well. So yeah, how it works, the lock is here, specifically kind of there, I guess. So that means when you try to, assign this a new value, this original one goes out of scope, tries to call delete on the data, And then because that's already locked, then it actually throws, or sorry, it doesn't throw anything. It actually causes a deterministic panic. So then you can use the debugger to work out, what's happened. So another one, where is the error here? Let's go through it. So we have a vector of bombs. We basically push back a bunch of bombs. And then for each time we construct a bomb, it basically sets this global bomb raw pointer and assigns it this. So in theory, after this one, last bomb should now be pointing to the new bomb we've created. It keeps happening. So by the end of it, last bomb should really be pointing to the last bomb that we've created. So again, we dutifully touch the bomb, and then, it prints out boom. Now, I'm sure some of you can see the issue with this, in that it doesn't do what we think it should do. Effectively, these are temporaries that are being created, and then they're copied before being pushed back into the bombs array. So you push back a copy, and then the original object goes out of scope. So essentially, last bomb is being assigned something that is a temporary that's literally just going to go out of scope immediately after this call, which means by the time you touch it, you're pointing at, memory that's effectively dangling. So let's run this example. Let's clear up a little bit there. This one is dangling temp 2. Got so many of these things, it's easy to lose track. So it's this one. So let's compile and run it. And there we go. You can see it's just, calling boom. Now, what's interesting is that this boom, we're not actually accessing the actual bomb itself. We're not calling, we're not accessing member variable like, name or something like that. So in theory, you'd think it should work, or rather it's very unlikely to crash. But it is still undefined behavior, which means the address sanitizer will not pick it up because you're not actually accessing any poison memory. And, really, that's not the worst thing. It's more the fact that a use after free is just waiting to happen because, it might be, printf for now, but later on, you might just chuck in sort of like to print out the bomb's ID or something like that. So it's really just, a problem waiting to happen. Apparently hardware assisted kind of setups can track it down, but again, I've not been able to verify that. So let's have a look at how C++ sys handles it. So if I compile it, run it, you can see we've got the good old attempt to destruct locked memory. So that one's handled it because, the mechanism is more mechanical. So we're basically pushing back, no, we do it here, sorry. When we try to assign the last bomb, rather than it being a raw pointer, it's now a sys pointer. So we assign that, so it's now locked. This temporary, gets instantiated, this gets called, but then when the temporary goes out of scope, if you recall, this sys pointer was basically a strict observer, which means if the object it's pointing to goes out of scope while this is still pointing to it, it'll literally just give a panic. Which is good. It means it sidesteps this issue completely. And then this one is a bit simpler of how it kind of works. So we're looking now at, effectively using iterators. And, can anyone spot the issue here? We can go through it. We push back some numbers. And then basically we just iterate through the actual, the elements. And we say, if basically the iterator is currently the first one, we then push back the number 5. So let's just focus on this one. Let's pretend this values arrays doesn't exist. As we've pushed back, potentially the backing store changes, which means the iterator there is invalidated. There's nothing there that is protected against that. So as we go on to the next iteration, we call it ++, but that's now effectively a dangling iterator. So that's no good. But then let's pretend this line doesn't exist and we go straight for this value arrays. We've erased the object that the iterator is referring to, but because we've forgotten to do it equals values.arrays, next time we do it again, it's potentially a dangling iterator. So to be honest, this whole thing's a bit of a mess, to be honest. So it's it's a similar issue to a dangling pointer. It's difficult to track. Microsoft's Visual C++ has like safe iterators in standard library, and this was a good step. And it's a much easier challenge, this one, because you don't need to kind of intercept anything. The actual iterator object itself can be the object that provides the lifetime lock. Yes, that's very expensive in terms of overhead, but again, because it's just in the debug, I'm not too worried about it. So, but when you do then, dereference the iterator to actually get the underlying object it's referring to, then yeah, you do then want to lock it because potentially the iterator might change while you're accessing it. So you've got a similar issue to the, the unique pointer being going out of scope or being destroyed when you're currently in the middle of accessing the data it's referring to. So, yep, that's that one. So essentially with C++ sys, we'll split this again into, it's basically two errors here. So the first one is when we try to push back, because the iterator is, effectively holding on to it, it'll give us a panic because, the iterator, we have an iterator that's, preventing us from modifying the memory. This pushback's trying to modify the memory, so it just gives a panic. This values arrays one. This line will succeed, but as soon as it tries to do ++ on the iterator, because the iterator's been flagged as invalid now, it'll basically panic on the next access. So when you call ++ it on it, it will panic. So effectively, by preventing any sort of dangling, we kind of sidestep really any risk, even risk that wasn't really being flagged by address sanitizer, just because you're quite strict, which means you do limit some designs, but effectively you sidestep so many issues. The whole thing happens at runtime, but because it's preventing some designs that could potentially be dangerous, it's kind of leaning back towards them static analysis. So I've kind of slightly cheesily coined the term, it's a runtime static analysis, but I don't know how correct that would be. So there are some weak areas, and in some ways the weak areas are useful to actually discuss because they're quite useful at explaining how the whole mechanism works. So firstly, the syspointer approach is very rigid, which means that a panic will happen if you try to destruct anything that has an observer, even something that would be completely safe. So a classic example is teardown, when you're closing the application, you don't care about anything really because you're not going to access anything, but you'll then potentially get a panic because effectively a pointer is still referring to some data. Even though you had no intention to actually access it again, it was going to be completely safe anyway, it'll still just give you a panic. So the best example here, or an example, is pretend in like a game, you basically have a renderer, and a renderer needs to know the texture it's going to, basically render, and then a mesh of, what, vertices and triangles it's going to render as well. So these are pointers because you don't really store them in the renderer. You might want to reuse this texture for many, many objects. Likewise, this mesh might just be a cube, and that's going to be used for loads of objects as well. So you don't Renderer doesn't own them, so they're simply observers. And then in player, you basically have this renderer, the texture, and the mesh. Let's just say the player, owns them all. So in the constructor of player, we assign the texture to be the texture that's in player, and we assign the renderer's mesh to be the mesh that's in player. And this will give a panic. And that's kind of weird, but if we go through it, effectively it's the order. So we're creating the renderer first, we're then creating the texture, then we're creating the mesh. Now, as we know, things get destructed in the opposite order that they're actually created. So the mesh will get destructed first, which means that, the mesh here is being held onto it, so that will give a panic. Then the texture is being destructed second, and again, that would panic as well, because, the renderer is still holding onto them. So the solution is really quite simple to, reorder them. So essentially the renderer should be the last thing. So the renderer should really just be placed here and moved here. And in some ways, I know this is a false positive, but it feels much tighter now, because it means that, as it destructs, that any potential cleanup code is now going to be valid. So if, let's say the texture had some weird cleanup code that relied on the renderer, you actually know that is kind of, now valid. So yeah, the renderer should be created after the mesh and texture. Otherwise, effectively, if the mesh and texture fail, you just have to immediately destruct the renderer again, which is kind of weird, a bit wasteful. I know though, in practice, that's potentially is necessary. As one example, the renderer might need to first be queried to know kind of the texture size. Let's say the renderer contains, whether your graphics card supports sort of like power of 2 textures or something like that. So you might need that to exist before the texture, but that's life. The biggest issue would be that texture or mesh might be in a different object entirely, like a cache, or you might have the objects stored kind of in a sibling object if you're looking at like an ECS system. But that's what weak pointer is for. Another slight weak error. So again, for safety, we have an object in there, a template type called sys0, which basically, zero initializes something in a structure. That's because it's so easy to get, to use an object or use something primitive before it's initialized. C++11 obviously allows you to initialize objects as part of the actual definition. And then sys0 really is there just to allow it for C++98, but that's not so important. The biggest issue, though, is that it's an upfront cost that will be permanent now. So, for example, int, the first one, this you have to set using the initializer list to 0, which is fine, but sometimes you don't know what the data should be at this point. C++11 allows us to actually include it within the definition itself or declaration itself. So that's now set to 0, again, a permanent cost. And then sys0, this will then be, set to 0 in the constructor of the sys0 object. But again, that is a permanent cost. That's no good. The better solution, or rather the solution that aligns more to C++ sys, or the vision behind C++ sys, is this sys unset object, which means it doesn't get assigned, but it has to be assigned before you then use it. So as I mentioned, zero initialization is a permanent cost, and in many cases, the value is going to be replaced with more relevant data anyway. So yes, you could take the risk and simply not initialize it, and then later on in the constructor or later on, then set it and just hope that, you don't use it before it's been initialized. But that's very difficult to verify. Yeah, so C++ sys doesn't want to zero initialize it. Instead, it wants to verify the correctness rather than prevent just kind of, or safeguarding against it. It would actually rather be able to strip it out in the release, knowing that you've actually gone through and verified it, at least during some branch testing beforehand. So yeah, C++ sys does have 0 in there, but it was a bad design. So now the sys unset is the way forwards. So another slightly weak area is shared semantics. So we don't have shared pointer just because there was no easy way to verify cyclic references. Plus, the standard implementation is perfectly good. If you want sort of like, very flexible observer patterns, go with that. But there is a sys weak pointer, and it basically stores its ref count in the base object or an auto pointer, which is, to be honest, very similar to a shared pointer. But it's this ref count that really should raise concern, because that has a permanent cost. So in most cases, the observer pattern is overkill. You just want it to not cause a panic, so you can't use sys pointer, but you don't really need to properly query and know if the object's been destroyed or not. So it is overkill. It's safe, but it is overkill. It's a permanent overhead, and certainly in multi-threaded environments, because of this ref count, the data inside needs to then be thread safe and atomic and things like that. So it is quite expensive. But it is so useful having this observer pattern, or be able to know when something's being destroyed, because with hierarchical layouts, this works exceptionally well with C++'s memory system, RAII, in that if you chop off an entire branch, all of the memory further down that branch cleans up. But back pointers, need to know potentially their parents, so you can actually have them as sys pointers. That's not a problem, because they'll be destroyed before their parents. It's the graph layouts that's the biggest issue, and this is the rationale still behind even supporting the weak pointers, because graph layouts require employees potentially to point to other employees, even though they're at the same level of the hierarchy. For example, some of the employees might be the manager of another employee, so they're effectively siblings, but they still want to point to each other. Or in a more game setting, players will target other players. They're all players, but effectively, when they destruct, it then matters the order they destruct, and you can't guarantee that with a lot of designs. So essentially, in short, sys pointer makes teardown of these graph layouts completely impossible, just because, if the object destroys while it's being referred to by another, employee or player, it will just give a panic. So we really want the performance of a raw pointer and the flexibility of a raw pointer, but we still want the verification provided by a standard pointer. That should be a sys pointer. There's no such thing as a standard pointer, sys pointer. But we don't want this overkill. So really, rather than having a weak pointer as it is now, we really should, the name's confusing, but we should effectively modify the weak pointer provided by sys, the sys weak pointer, and instead simply cause a panic if you try to check its validity. So for example, if the object's been destroyed, so if it's shared ref, if the object it's referring to, its shared ref is 0, as soon as you try to access it, even to compare its value, it should really just give a panic. That way it prevents the validity checks becoming part of the logic, and that means in debug mode you can ensure that you've used sort of like a different mechanism to check for validity. That may well be used in the standard weak pointer rather than the sys weak pointer, but it just means then you can actually then strip out all of this upfront cost from it in the release mode and still know that you've prevented dangling pointers. And this has the benefit that even then a sys vector could actually offer this kind of shared ownership setup verification. Yeah, most importantly, zero overhead. Yeah, I explained that really badly. But anyway, let's carry on. So iterator locking is another weak area. It's a bit too strict. So here, there's two examples here. So this one, we push back a bunch of values. We erase, from this position to this position. Now this would be no problem if this was vals.begin vowels.end. But because we do +2, it basically creates 3 iterators, one of them being a temporary, which means that when this tries to erase, these 2 get invalidated, but the third one that's a temporary holds on to it, so you get a panic, which is lame. The solution to that is to store the 2 as a separate iterator, so the temporary goes out of scope here and doesn't become a problem anymore. And then you can call vowels arrays, begin and then 2. So that's a workaround, but it's not great. So essentially, to best leverage C++ sys, you want to just ban raw references and pointers. I know that's easier said than done, but it simplifies the verification model. It means you can basically just correct for them. Likewise, to return sort of vectors and containers, we should be returning iterators or sys span, which doesn't yet exist, but that would be a better solution than returning a reference to a vector. Yeah, essentially, one benefit though is that it's perfectly safe to have a raw reference or a raw pointer as a parameter to a function, because this is always being inevitably locked at some point during the access. So as soon as you are in some func and you have a reference provided into it, you know that the lifespan of that reference will be absolutely safe, or there'll be a panic. There'll never be an invalid access of that reference. C and drop, with literal, C libraries remains, fairly unsafe, but that is the same with Java, Rust, Ada, all of the languages. Just because, they tuck it away into bindings, I don't think you'll ever be able to get completely safe undrop with C, unless you maybe compile C with, mscript and then run it in some sort of node VM or something like that. So in general, though, you can actually leave C++ sys on, at least for the first few kind of builds for your client. It has less overhead than address sanitizer. I would say leave it on for early releases, to the beta stage at least, maybe even some of the early production stages, just because it's fast enough. And it means that you get good error messages. It doesn't just kind of sometimes crash, sometimes not. It'll always crash. Maybe turn it off for stakeholder demos though. I think some memory being corrupted but not crash might be the better solution to the crash. I don't know. But also, once it's been confirmed and you are happy to then finally strip out C++ sys, effectively you can mark it down as an instant optimization package to your client. So importantly then, multi-threading, it's not at all thread safe, but it doesn't really have to be. I know this is debatable, and we do have a thread safe version, but I want to avoid that because it adds complexity. But essentially, verification occurs in debug mode, and you can then just have one thread in debug mode. I know it'll be very slow, but there's no reason you need multi-threading in the debug versions. The debug versions are there to verify it rather than have performance. So in release mode, it's completely thread safe because effectively it's been stripped out completely anyway. There's no kind of reference counts or anything like that. This does slightly conflict with the previous slide in that, if you leave it in and you tell the client, oh, but you also can only have one thread, they won't like that. So yeah, it is nuanced. But yeah, it does simplify again the model slightly. So we're coming to the end. Effectively, it's been used in a fair number of projects now in different areas. So it works quite nicely on Windows. You can see in the corner here. We've got on mscript, and it's really not a problem because it's completely agnostic C++. It can support any version. It doesn't have any other real dependencies. Here it's OpenBSD, so AMD 64. This one here is Linux. And then on some of the more interesting ones, this is just AVR, just bare metal GC AVR. And then this is Zephyr, so this is on ARM64. So it can run anywhere that a C++ compiler can run or compile to, it can also target. So yeah, there was a lot there. Thank you for listening. I'm very happy to take questions. I think it's a great technology. I try to use it as much as possible just because it's it's so liberating being able to kind of, write some code, a substantial amount of code, and then not think, oh, somewhere there's a memory error just waiting to kind of rear its head and crash just when I'm trying to show someone. So it's a cool tool. It's open source, BSD license, so do check it out, have a play with it. It's intentionally kept minimal. It only really focuses, as I mentioned, on the safety aspects of the C++ libraries. But certainly, any additional work, I'm very happy to collaborate with it as well. So yeah, thank you very much. And after this, I think I'm going to be on GatherTown as well. So I need to quickly log in and then answer any questions. Thank you very much.